So, welcome everyone to the fifth lecture in Mathematical Statistics in the winter term 2023-24. You see here the new version of the list of exam questions of the lectures, and as I have promised the last time, or told you the last time, I am at the fifth question where you have to show the theory 2.2 of the lecture. But we did the last time. You have x1, x2, and so on are IID, are new variables. U is the distribution of x, U is the empirical distribution of x1 to xn. A is a set of sets, A subset from RD. Then you have to show that you have for all n and all epsilon greater 0 the probability that the supremum over A in calligraphic A, absolute value of U of A minus mu of A is greater than epsilon is less equal than A times the n shadow coefficient of n, A times e to the power minus n epsilon squared 32. And there's a long hint on this. So basically the proof is given because it's described what you have to do in the 4 steps. You make a symmetrization by a ghost sample, you introduce random signs, you condition on the xi's, and you apply the inequality of everything. So it's rather easy because I show you what the proof is, but the difficulty is you have to fill in all the gaps here in details. Okay, that's the first thing. Second thing, what did we do last time, or where are we in the lecture? That's this slide, which I want to show. What are we doing today? Well, we have seen if we have IRD random variables x, x1, x2, and so on with values in RD. U is the distribution of x, mu is the empirical distribution of x1 to xn. Then by Klimenko-Cantelli, we know the supremum over all x in RD of the absolute value of mu and of the interval of minus infinity of x minus mu of this interval converges to 0 almost surely. And this you can interpret as this empirical distribution enables you to estimate the probability of intervals rather well. Now you can ask, okay, if I don't just want to make statistical inference about values which are in intervals, but about more general sets, can I replace the intervals above maybe by all measurable sets in the above supremum, and then the first statement, okay, this looks like a scanned document, that's correct, but I don't want to make any changes in it. And the first question is, okay, what about if you replace in the above supremum the supremum over all intervals by the supremum over all Borel sets? Then for the empirical distribution, this does no longer converge to 0 because as one of the sets you can insert here the random set x1 to of the xn of your data points, and there mu is 1, but if mu has a density with respect to the Lebesgue measure, this is a finite set which has measure 0. So the whole thing, the difference is 1 and does not converge to 0, actually. And then the main point, what we are doing today is, I want to show you that even with a better estimate, even if you try to improve the estimate, it is not possible to construct an estimate such that you can, in this distance, which is called the total variation distance for measures, so the supremum over all b and bd of the absolute value of the estimated probability minus the true probability that is converged to 0 almost truly in all situations. More precisely, the theorem says that there does not exist any estimate mu in hat, which is an estimate of x1 to xn, as a function from Borel sets to R, satisfying supremum over all b in the Borel sets of absolute value of the difference of mu in hat of b minus mu of b converges to 0 almost truly for all distributions mu on RD, BD, and I did not write this on the blackboard 2 lectures ago, but basically one could add here and all IID random variables x1, x2, and so on with px1 equal mu. So in particular, then you see what the correct mathematical statement is. The correct mathematical statement is the negotiation of this one. So if you make the negotiation, then for any sequence of estimate u and hat, you find a distribution mu and RD, BD, and you find ID random variables x1, x2, and so on, which are distributed about like mu. So that if you apply this estimate mu and hat to these n random variables x1 to xn, and use this as an estimate of b, then this supremum over all b and bb of mu and hat of b minus mu of b does not converge to 0. That's the point what we want to prove here. And as I promised you the last time, and you can see already there are this time less people than the last time, so I guess maybe the promise was not so good. As I promised you the last time, this proof is a little bit more involved than the last proof, which we had, and the last proof was already wrong. On the other hand, I think it's a beautiful proof. It has some nice ideas in it, and it was published beginning of the 1990s in Annals of Statistics. Annals of Statistics is the flagship of the mathematical statistics, so it's considered as one of the best journals in mathematical statistics which we have. The proof was given by Luc Defroy from Montreal and Laszlo Györfi from Budapest. I know both of them personally. And it's a nice book. It was a short paper, but as you see, okay. Maybe I will stop talking and start proving. That makes sense. Okay, let me stop it here and start with the proof. And it's a long proof, and I'm a little bit afraid that I will not finish it completely in this lecture today. So the last part of it we will make on Monday, I guess. First of all, I will prove this thing only for d equal 1. And I will claim that it's without loss of generality, I can assume d equal 1. So I show that for a distribution on RB, so on the one-dimensional Borel sets, if you estimate just the distribution of RD, then for any sequence of estimates, you can construct a distribution such that this assertion holds. And if you consider the general case, so if you have shown it now for d equal 1, how do we get from this to general case? Simple, you use you have proven it for the one-dimensional case, and now you have a distribution on the one-dimensional Borel sets. You extend it to a distribution on the d-dimensional Borel sets by just using the value of this of a one-dimensional of this. Or by just if you have a one-dimensional value of x, you replace it by x by the vector x and 0, 0, 0, so that you get the value in RD here. And you use this distribution and apply your d-dimensional estimate to the straightforward extension of your one-dimensional sample to get a sample of this d-dimensional distribution by just to adding to xi, you add this d minus 1 times 0, and you get a sample of this new distribution, and then you show that basically with the d-dimensional estimate you can estimate this one-dimensional distribution, which is not possible. But I don't want to go into details here. Just believe me without loss of generality. Then what we will show we will show for any sequence of estimates mu and hat from B to R. And these are estimates which depend on our sample x1 to xn. Then not from the Borel sets to R. There exists a distribution mu 1, satisfying well, what we want to show is that the supremum over all, I need a little bit space here, supremum over all A and B you will hand of A minus mu of A. We want to show that this does not converge to 0, almost surely, but we show instead something much stronger. We show that this value is for all n greater or equal than 0.45. So we show that the infimum over all n and n is greater than 0.45. And surely, and you will see in the proof that 0.45 comes from. Of course, you can produce here also another number, but we will show it for 0.45. And how to do this? Well, the first idea is we will define in a clever way a class of distribution. This class of distribution will depend on a parameter, and as a parameter we will use an infinite sequence of 0 and 1. So I will give you a parameter, and then I will depending on this parameter, I will define a distribution. It will be our first step. Then I will show you that I can use, due to the way I construct my measure with parameter b, I can use the estimate which I have to reconstruct the parameter values. And basically, we will show that if this supremum here is greater or equal than 0.45 times the indicator that any of these parameter values is reconstructed in the wrong way. That will be the second step. And then, well, we are in statistics or in probability theory, so basically we will use a trick, we will randomize. We will choose our parameter randomly. So instead of a fixed parameter, which is an infinite series of sequence of 0 of 1, I will just use an infinite sequence of random numbers from 0, 1, where the components are independent and uniformly distributed in 0, 1. And then we get a sample of this distribution and reconstruct the parameter with our estimate. And then the point is we will show this is not possible. So with probability 1 we will make an error by reconstructing this parameter, and then we will prove the result. Because then we have a random parameter, so that with probability 1, if you use this random distribution, you get a total variation distance greater than 0.45, but if it's probability 1, you have one value, then there must exist one value. That's it. And for this point where we show that this F is not possible, we have somehow to determine the best possible estimate. Okay, so let us start. Step 1. So for given B in B, that's a J n. That's an infinite series of 0 and 1. Define B. And I have the random variables x1 x until the xn. Is px1 is equal to u. We start, okay, how do we define mu b? Well, we start by defining in a complicated way a uniform distribution on 0, 1. We construct this uniform distribution on 0, 1 by just constructing the decimal representation of a number, where we choose all the digits by IID random variables uniformly distributed on the possible digits between 0 and 9. And then we use this parameter b in such a way that whenever you have b equal to 0, you set the corresponding digit to 0. And this gives you a distribution. Okay. I start with these random digits, and I define these random digits also for x1 to xn. So I need a lot of random variables, y1, y2. And then that's for x, and then for x1 I need y11, y21, no, y12, infinite sequence, and so on. And I use them IID and uniformly distributed on the set of possible digit values 0 to 9. IID and the variables uniformly distributed. And then I define my random variables depending on b. And I define a random variable x depending on y and b. So these infinitely many uniformly distributed digits, y1, y1, y2, and so on. And this vector b by just using k equal 1 to infinity yk times independent function that the k's component of b is 1 times 1 divided by 10 power t. And then ub is p xp, xy, p. And now I define my sample set. Oh yeah, I have forgotten my y's. Sorry for that, guys. Y is y1, y2, and so on. yi is yi1, yi2, and so on. Then you define x1 as x b y1b, x2 is x b xy 2b, and so on. And you see x1 to xn are IID with distribution to b. So that's my distribution and my data. distribution x, y, b, can you tell me what kind of distribution do I get, depending on b? So can you give me any example where you can say, okay, if I choose b in this special way, then I get this distribution? Any idea? So you can choose this infinite vector of 0 and 1s b, and if you choose it in a special way, you should tell me what mu b is. What kind of distribution?
If you choose like b to be only once, then our x is like it's like a random number between 0 and 1.
Yes. Yes. So if you choose b containing only ones, then you just get a uniform distribution of 0, 1, on the interval of 0. Okay. Good point. First point. Do you have another example? Any other possibility? If b is only 0, then you get what? The random variable is 0. So if b is only, if all components of b are 0, then the value of the random variable is already 0, so it will be a direct measure of the point 0. Correct. Okay, that was the second easy. Now, one more, which is a little bit more complicated. B is neither only zeros, or neither all components are zeros, nor all components are 1. What can you say then? Any example? Maybe the easiest example is if the first component B1 is 1 and all other are 0. What do you get then?
Then it is just a random number of 0.1 to 0.0, then 0.1 up onto 0.9.
It's a random number which takes on the values 0, 0.1 up to 0.9, and more precisely it's uniformly distributed on this finite set of values 0, 0.1, 0.2 until 0.9. So it's uniformly distributed on 10 values. And in the same way, you can see if B contains finitely many ones and otherwise only 0, then it's a discrete distribution. And each time the number of values, if you have one more value where you have 1, get up by a factor 10. Okay, the other point is, what about if all of the b's are are 1, except one of the b's is 0. So, for instance, if you put the first value of b, first component, to 0 and all other to 1, what do you get then? What kind of distribution?
It's again a uniform distribution, but on values between 0 and 0.09999 and so on. So technically,
it's a uniform distribution which value in Bitcoin on 0 and 0.999.
0.0 and then only 9. So the first digit is 0. Then after that, the maximum possible is only 1.
Oh yeah, yes, because it's uniform distribution on an interval of length 1 divided by 10 here. And then more difficult if you have 2 times 0, but all others are 1, then you will see it's a uniform distribution of union of a on a set which has Lebesgue measure on the first was a uniform distribution on the set of Lebesgue measure 1 divided by 10, and if you have 2 times the 0, then it will be a set of total Lebesgue measure, but it will be set consisting of different intervals, which you can put together and get one set, and that's the support of the probability measure, and it will have the support will have the back measure 1 divided by 100, and so on. So you see, if you have, what did we know? Now we had finitely many ones, then you have a discrete distribution, and finally many zeros, then you have a uniform distribution on some set where the back measure goes down. And the difficult part is if you have the same, and the first step is discrete, the other one has a density with respect to the back measure, but the difficult point is, but it's not necessarily this here, but the difficult point is if you have at the same time infinitely many ones and infinitely many zero, then you neither have a discrete random variable nor a random variable which has a density with respect to the back measure. The second one you see because the back measure of the support will go to 0, or will be 0. Then you cannot have a measure. And these are the hard estimates which we cannot reconstruct, or we cannot reconstruct this. Okay, first point. Good, that was the first step. Questions so far? The second step, we use our estimate U and hat to reconstruct E from x1 to xn. How to do this? Well, we consider the set AK consisting of all numbers in 0, 1, where in the decimal representation of this number, in the case position, there is a 0. No, there is a 1. No, there is a 0. Okay. So we make this one. Equal 1 to infinity, xj divided by power j, where xj is in 0 to 9. Okay, and the important condition is the case position xj is 0. We consider this set. And then we look at what's the measure of mu b of this set AK. I want to compute this measure. Well, you just look at it. It means that this mu b is the same as the probability of B of AK that X is in AK, or X, Y, B. So that's the probability what was X, Y, B. So we just write down the formula, which was this infinite series, YK, indicator function d of k equal to 1 times, oh maybe I should not write k here, let me write j here, because we have our set, ak we use k, sum j equal 1 to infinity, yj times indicator that the j's component of E is 1 times 1 divided by j, that's in AK. And now I claim that's just the same. That this k term here in the sum is 0, which means that yk times the transfer function of ek equal 1, and this one is 0. And if you look at this, then of course, if this condition holds, so if this event holds, then this event also holds. That's obvious. And the other way around is not true. If this event holds, then this must not hold, because the decimal representation of a number is not unique. There could be, you could write 0.1 or 0.09999 forever. But this occurrence of the 99999 forever, this occurs only with probability. I mixed up my notation, sorry for that, because it's also a mistake here, yeah? Because you don't use this yk, you use this one. Sorry, that's your mistake, and here we have a yk. We look at the case components or chase components of this infinite sequence of digits, which are represented by y. And that such an infinite sequence, 9999999 and so on, that occurs only with probability 0. Because you have to choose infinitely often the 9. So events have the same probability. Which is what I've written down in words, in formula in words here. Not a good explanation, but I think you see what I mean. But it's, you can make yourself clear, it's the same. That's the first point, and now you can easily compute this probability. What about this probability? Well, you distinguish two cases, and either bk is 0 or bk is 1. Or bk is 1.
Is it fine for asking questions?
Excuse me?
Is it fine for asking questions in German?
Yes, of course.
Was habt ihr vorhin nochmal gesagt, mit welcher Menge impliziert die andere oder enthält die andere?
What did I say about which event contains the other event? Well, if this event holds, if this is true, then of course this number has exactly this form here. So it's easy to see that this event here is a subset of this event. And therefore this probability is greater equal to 0. But the other cases where it's not equal, that means that infinitely many 9s must occur. And that happens with probability 0, so therefore it's 0. It's the same. Okay, now we want to compute this probability. Can you tell me how large is this probability if the case component of B is 0?
The indicator function is 0, and therefore it has probability 1.
The indicator function is 0, and therefore here you have 0, 0, so it's probability 1. Right. What about the other case? If bk is 1, then the indicator function is 1, and then probability is maybe someone else? 1 divided by 10, because yk was uniformly distributed on 0 to 10. Now you see, if you look at the new b value of the set k, you can clearly distinguish between the case whether the case component of b is 0 or 1. And then, if I give you an estimate, and my estimate is in your head of ak of this probability, how do you construct an estimate of b? Well, very simple. You look at your value won't be 0 or 1 or 1 divided by 10 here, because it's an estimate. The estimate has some kind of error. But the straightforward decision is to say, if this estimate is closer to 1 than to 110, then you predict 0, otherwise you predict 1. And that means that we use mu and hat. We use, how do I note? P and K hat as an estimate of pk. Well, I estimate 1 if what? I told you if the measure of mu n hat ak is closer to 1 than to 1 divided by 10. So if it's greater than the arithmetic mean of the two values, and that you see is 11 divided by 20, and 0 else. And then we use this one to reconstruct pk from x1 to xn. And you see, in this way, I can, with this example x1 to xn, I can reconstruct all components of B. I have an estimate for all components of B. And now I make a relation between the total variation distance of mu and hat and the errors I made with this estimate. And that's the next point. We showed it mu and hat of ak minus ub of ak, the absolute value, is greater than equal than 9 divided by 20, and that's the magic 0.45 from our proof, times the indicator that our estimate or reconstruction makes an error, pk hat not equal. And this is actually rather easy to see because this holds. Well, you just consider different cases. First case is that your estimate is the same as the number to be estimated. P and k hat is equal to bk. If P and k hat is equal to bk, you have a question?
Yeah, I have a question to the P and k hat. I think the 0 and 1 should be swapped.
The question between B and K hat, you think the 0 and the 1 should be swapped. I said it's correct. I said 0, or I said I predict 0 if this is closer to 1. You are perfectly right. I would have seen this now, yeah. It's a good point to ask this question because it was the last moment before I recognized it myself. That's usually the right thing to ask, to wait until the proof fails totally, yeah? And then you ask the professor, but not before, yeah? It's okay. because it's your last option to ask, yeah? And you can, and this leads to the maximal confusion of the guy if he does not understand the proof. But thank you. You're right. So we change it in this way because we predict if we are closer to 1 than to 110, then we predict 0. It's perfectly all right. Okay. Now I want to prove this relation, and here I will read now the definition of the estimate. Oh, by the way, it was a little bit too early. We should have waited until I'm confused and then. Okay, if you consider this case, yeah? If we are in this case, then this indicator is 0, and of course the absolute value is greater equal to 0. So that's okay. So let me give case 2. Also we have we have now the case that they are not equal to 0, and we compare them separately. The first one is that one is which one should be 1? Or maybe make this is our bound ENK net 0 and dk is 1. What can you say about mu n hat, absolute value of mu n hat? AK minus B of AK. Well, because B of K is 1, you know that mu B of AK is 1 divided by 10. But this one will be greater equal than 1120. So it will be larger than the one. So I can forget about the absolute value. And I can say this one is greater than 11 divided by 20 minus 1 divided by 10. And that's 9 divided by 20. And then the case 3 is similar. E and K hat 1, K 0. If we look at this way, then P and K hat will be 1. So P and hat will be 1. No, if it's mu and hat, P and hat is 1, then BK is 0, then BK will be 1. Although, if BK is equal to 1, then mu of B of AK is 1. So this one is this time larger, so we have 1 minus this, and this is 0, so you are here, so this is less equal than 11 divided by 20, so it's greater equal than 1 minus 11 divided by 20, which is 9 divided by 20. You have a question?
Yes, I'm confused because in the lecture notes it says P hat and K, the second component is 1 over 10. We have like 0 at the top and 1 over 10.
It's a typing error.
I'm not sure. It's a typo.
You have the German lecture note or the English one? Or?
It's the German one.
The German one, there should be a typo then. Yeah.
Okay.
So that's definitely, you have to predict 1 or 0.
Yeah, okay.
Otherwise it makes no sense. Okay, so I don't have space here, so let me just write similar. As you see, yeah? So we have this. And maybe I can write one more thing on the blackboard before I make a break. In this wonderful proof, consequently, what do we have? We consider the supremum over all b in 0, 1 to the power n, the infimum over all n, and the supremum over all a in b, mu n hat of I minus b of a. And you remember what we wanted to show, that there exists a b such that this value is greater than 0.45 almost surely. And I showed that the supremum is greater than 0.5 almost surely. Now I replace the supremum over all a and b by just considering the sets ak, which I have defined before. So that's greater than, if you keep the first supremum, make it not just before the infimum over all n, but make the supremum over all k. And that of ak minus uv of ak. And we have just seen this nu and hat of ak minus uv of ak is greater equal 920 times. And that's I plug in here. And I move this factor 920, which is the 0.45 in front. Supremum over all b. Infimum over all n. Supremum over all k. Indicator function that my prediction, which I have defined before this p and k hat, is unequal in 2 value. And actually, I don't use this equation to prove the theorem. It would be a kind of problem, because if I show that the supremum is greater or equal than 0.45, then I won't have that there exists a value which is greater than 0.5, because I don't know whether the supremum is really attended. But we will show instead that if you are plugging here a random value for b, then the value will be almost surely greater than 0.4. But it's only a minor difference. Okay, questions up to this point? Please?
Can we get like another constant if we use like different bases? Because
Can you get another constant like you use a different basis? That's a very good question, and that's a homework for you. But how can you improve the constant? But yeah, on the other hand, you don't need to improve the constant here. But I'm quite sure that if you use the basis 2, you will get something different. Maybe you will get a smaller constant with basis 2, and if you use the basis 100, a large constant. But I'm not sure. In one way, yeah. One way.
I don't think it works with basis 2, because then we have like only 2 cases with the 0 and 1s.
You don't think that 2 works?
I think we
I haven't thought about this here. Another homework for you. I'm happy if I can present this difficult proof here, and you understand it, and I don't want to improve this proof here. It's interesting, but I'm sure I know Lars Photography and Luther Roy, both of them here, and there's no chance to improve their proofs. At least not for me here. I'm sure that you can improve. I was feeling when I was writing down this lecture notes, I was sure that I can improve this constant here. But it doesn't really help. But you see where this 0.45 this magic came from. It was the difference between the average of 1 and 1 divided by 10 and the two values. And I think if you make a basis 100, yeah, it will be larger, yeah? Because you have the difference between 1 and 100, yeah? The difference between 1 and 1 divided by 100. And you think for 2 it doesn't work? And why do you think that for 2 it doesn't work for 0 and 1?
Because then we have like only in the mu b, then we have 1 and 0 because if
okay, you think you can't see the difference.
Because we only choose randomly between 0 and 1, and then we have, if it's not 0, then it's clear that it has to be 1. Then it's not random anymore.
If the bk is 0, then it's, well, it depends on the probability. Yeah? If the bk is 0, it will be 1, and if its bk is 1, yeah? But it still has to be 1, it's the probability 1/2. Yeah? You have the two different probabilities, you had 1 and 1/2.
Yes.
And then, of course, your distance is only 1 minus 1 divided half, and the number will be 1 divided minus 1 divided by 1/2 divided by 2, which is smaller. Yeah? And you see, in this way, we could go up until 0.5, and then the next question would be, can you go more? Can you apply it in 0.5? There's nothing to win here, because the paper is already published, and you can spend years with this, making this proof, and improving this constant from 0.45 to 0.99. Okay, it's difficult proof. Doesn't help. Okay, any more questions? So then it's 10:43 on my clock, and I will clean the blackboard and we'll go on 10:48. Thank you. So I would like to go on with the lecture. We come to step 3 and step 3. 3 means choose the value of b randomly. And I use for the random value, I use a capital B. And I just use an independent, or I use an infinite sequence of independent 0 and 1 values, uniformly distributed as 0, 1. So B is the B1, B2, and so on. And these components are independent, uniformly distributed on 0, 1, and independent of all other random values which we have already introduced. We have B1, B2, and B1 are I and D. Uniformly distributed on the and independent from our y random variables. Yij, Ij. This was all the randomness which we used to create our distribution x1 to xn. And of course, I also make them independent of Yj. This one. N. Of course, I need this one too. Then what we make next. The supremum over all even 0, 1, n, the infimum over all n, supremum over all a and b, mu n hat of A minus mu E of A. This guy was larger by step 2. Then 9 divided by 20 times the supremum over all n, the infimum over all n, the supremum over all k, indicator function that our estimate of pk is wrong. So p and k hat not equal to pk. And here our estimate is chosen depending on the sample x1 to xn, and the sample x1 to xn depends on the vector of small b here. So it's in x, the x y1b until x ynb we are plugging small b's. And now I plug in, instead of the small b, I plug in the random b, and then of course the supremum is larger than the random variable. 20, forget about this. Infimum over all n, infimum over all k n, indicator function of p and k hat not equal to pk. And this estimate now here depends on x y1b until x ynb. And in contrast, the other line above, the estimate depends on the x values where the capital B is addressed by the heuristic model. And that's equal to 9 divided by 20, and this infimum over the rest I denote by Zn. That's Zn is the rest, so it's a supremum over all Kn. Indicator function b and k hat not equal capital B. And what we do here is we use our sample xy1b until xynb to construct an estimate of these all components of B, these infinitely many components of B. And our error, or this describes that there occurs an error in any of the components. And what we will show in the sequel, it with probability 1, there will always occur one error. And then we are finished, because this will be 1, almost surely the Zn. So it suffices to show Zn is equal to 1, almost surely for all the and of course, this implies that you even have Zn like 1 for all n almost surely. So with probability 1, all of the Zn will be 1. So with probability 1, this infimum over n and Zn is 1. So with probability 1, you have this lower bound 920, 0.45, and that's it. And if you have this probability 1, this lower bound for some random value, then there must exist one infinite vector of 0 or 1 where the value is greater or equal than 0.45. Okay. More questions? Up to this point? So, I defined the class of distribution depending on the parameter. I used my estimate, for which I control the error and total variation, to predict this parameter. And I have to show that in this estimating of the parameter, given these random variables, I always make a mistake. It's probability 1. And that's it. And next we have a new prediction problem. I give you these random variables here, which are this masked decimal representation of a uniform random variable, uniform 0, 1. And you want to predict whether some of the components are set to 0 or which components are set to 0 and which not. And I give you n values of it, and you want to say, okay, from these n values in this infinite sequence, which components do you have to set to 0 and which not? And I will show you this is not possible without making at least one error. This will be one. So next is step 4, proof of the assertion. The theory. So we show for each element n that the probability of Zn equal 1 is equal to 1. Question?
Yes, I have a short question. Maybe I didn't get a point, but our goal is to show that, or our assertion is to show that the infimum of the supremum of mu n hat minus mu v is greater than constant.
Yes.
And on the board you have written that we want to show that the supremum of the infimum of the supremum is greater than constant.
Right. You just. I want to show that there exists a constant such that this infimum over the supremum is greater than 0.45. On the board, I write that I show that the supremum over all b values is greater than equal 0.45, and this you are right. This does not really imply that there exists one fixed value where it's greater equal 0.45, but there exists a value where it's greater equal than 0.44. But in fact, by my way of proving, I show that for a random value, this value is always greater than 0.45 with probability 1. And if it's with probability 1 always greater than 0.45, then there must exist one value where it's greater equal than 0.45. But in fact, how I write it down here is not totally correct. Yeah? Sorry for that. So I either should write something like 0.44 or make the argument here. But I've just seen this when I was reading it out. But you're right. But you want to see how the proof is working. Yeah? So what we have to show now is that for all n we have the probability that Zn is equal to 1 is 1. Fix n in n. And what I make, I want to prove that this probability is 1, and I give you a lower bound of this probability. We start by making the supremum by just plugging in the definition of center here. Given n in n, no, it's a supremum k in n. n, sorry. K and n indicator E and A hat not equal dk. Well, you rewrite the supremum as the union of events. Union of K and N of the event that E and K hat is not equal dk. Because if this event happens, or if the event occurs, yeah, then one of them, for one index, this indicator is 1, and then, oh yeah, but I have to write equal to 1, sorry. That's not what I want to write here. So if the event below occurs, then one of them occurs, then one of the indicators is 1, then the supremum is 1. On the other hand, if the supremum is 1, then one of them indicators must be 1. Because otherwise all of them are 0, then the supremum will be 0, and then one of them is 0. So it's the same. And now I forget about this infinite. This is a union from k equal 1 to infinity, and I use the continuity of the probability measure from below to rewrite this as the union capital and to infinity probability that k equal 1 to n. Only finite value of them, one of them of course. So we are here. So continuity of the probability measure from below. Here's this one. And this is basically the same that this whole vector of the Bn hat 1 to Bn hat n is not equal to the vector of the B1s to Bn. And that's the prediction problem which I consider next. So I predict only finitely many of these components of P. There's one bracket missing here. And I want to derive now, next I derive lower bound from this probability, which depends on n, and this lower bound will converge to infinity, to 1. Then we are done. Okay, let's do this. Consider this probability, so we write this probability again down. And that's somehow the tricky part of the proof. Despite that you have to have this idea which kind of distribution you use here. And now I have to determine a lower bound, and for this I determine the optimal predictor. But the optimal predictor, maybe in a setting where the optimal predictor has a lower error than this setting. You will see it in a moment. The probability of this is 1 minus the probability of the event that it's equal. And this probability of the equal I write as an expectation of the conditional probability. And I can condition on anything. And straightforward thing would be to condition on the data which I use in D and K hat. So x, y1b until x, y, and b. But instead I condition on a little bit stronger thing, so I give my estimate even more informations. I give them these components of x, y1b until x, y, and b. So we condition on, that was what I meant, that I consider a problem where I have more information available and derive a lower bound for this. And then, of course, I will also have a lower bound for the problem where I have less information available. So I condition here on these components occurring in my representation. These are the yik times indicator that bk is 1, and I have k in n and I between 1 and n. So we have this one, and then I also close the expectation.
It should be that the conditional probability of them being equal, right? Not unequal.
Yes, it's correct. It's I went from the probability that they are not equal, these values, to 1 minus the probability that they are equal. And then from the probability I make it correct. Now what do I do here? I give this is the probability that it's correct, so I give an upper bound on this probability. I somehow, so for this estimation problem, and this time I changed my data a little bit, yeah? I give a little bit more informative data, because I don't just give you these numbers, but I give you the digits in the decimal representation of the numbers, which is a little more information. And I determine next the optimal predictor for this one. Or more precisely, I will determine a predictor which is better than the optimal predictor, and then use this as a you will see. You will see. And if you consider this now, well, if I condition on these values, then basically all these guys are fixed. So I forget about these values being random and consider the probability only for fixed values. And that's what I next found. And I use, instead of the estimates, now fixed values. We want to equals to 0, 1. Consider the probability that n is not equal, no, is equal, what's the equality? Is equal to capital, yeah, it must be in, another writing error, sorry guys. That's awesome. Capital N, and that is capital N, but it was not using. And I condition on my random variables here, and y by k times indicator function bk for 1, and I have 1 less equal I. And n. Okay, then what comes home from this? This tricky arguments, I argue that these components of B1 to Bn are independent, and therefore the probability that they jointly take some values is just the product of individual probabilities. So I go down to the product. The product goes from k equal equal to n. The product of bk is equal to capital BK and condition on yik as indicator function bk equal to 1 of 1 is equal to I. Independence. And if you think about it, then you immediately see, of course, this is true if I would not have a conditional probability. So if I skip all the conditions, then everything is fine. But of course, I have a conditional probability, and why is it still true here? It's not so obvious. But what you basically do here is you, I wrote this as a non-elementary conditional probability. This is a general conditional probability. You use the factorized conditional probability. So you give here complete values, call them Zik, for these things, and show this for these concrete values. Then you use that this factorized conditional probability is basically an elementary conditional probability in this case, because the event that this occurs here has probability greater than 0. Then you rewrite it as a fraction, probability that both happens divided by the probability of the condition. And then you regroup in the probability in the probabilities these random variables such together, such that all these random variables occurring here are together in the nominator. And then they are independent from the rest. You use that the probability is a product of probabilities. And in the denominator, you can also regroup these guys here, or all the values by these guys here. And then you regroup the products and we interpret the fractions again as conditional probabilities. And somehow magically also a lot of conditions disappeared, because all conditions where k is greater than capital I disappeared. But that's not surprising me, because this will occur as a factor in the nominator and the denominator. So in fact you can prove this, but maybe it's better just to believe independence. Okay? If we are here, then we want to maximize this thing. Well, this thing is maximal if and only if all the terms in the individual products are maximal. Which is maximal if only if all factors are maximal. Then you use, what do I use then? So I know what is the optimal prediction here. For which value of pk is this conditional probability maximal? Well, its possibility values for pk are 0 or 1. And 1 you choose if this probability that pk is equal to 1, given these random variables, is greater or equal than 1/2. And 0 you choose if it's less than 1/2. So you can immediately write what the optimal predictor is, depending on this conditional probability, and that's what I use here. So I use that, I can plug in here the optimal predictor, the probability that Pn hat, Pn n hat is not equal to P1 that's greater or equal. Well, if I plug for this Bn1 hat until Bn n hat, the optimal predictor, I call, or I use the notation capital Bn1 bar until Bn bar not equal to B1 Bn. Where is Bn j bar this is 1. If the conditional probability that pk is 1, given my random variables, my random variables are yi, j, and pk are pk 1, and I is between 1 and n. If this is greater than 1/2, then 0 is. Okay, I use a few more minutes. You will leave them. I will leave them to you back next time. I cannot finish this proof, but I have to finish this proof for today in such a way that it's easy for me to continue this proof. And otherwise, I have to start with the whole step 4 again, which makes no sense. So I have to tell you what I show in this equal, which implies, and then we will show the next time just. Yes. So basically what we do next time, we compute this conditional probability, which you see on the upper backboard on the right side down, on the lower part. We will compute this conditional probability, then we will determine what B and J actually is. And then, when we have this B and J bar, we will compute this probability. So we will show on Monday. I will show that this probability of Bn 1 bar to Bn n bar is not equal to B1 to Bn. We will show that this probability is greater or equal to 1 minus 1/2 times 1 to the power divided by 10 to the power 10 with exponent capital N. We will show this one by basically combinatorics. Which implies if you look what we did, we had this probability that Zn is equal to 1. This probability that Zn is equal to 1, it was on this, unfortunately, on this other blackboard, which I have already cleared. So this probability was the limit that is Bn from the probability that the Bn1 hat until Bnn hat is not equal to B1 to Bn. And then the limit n tending to infinity. And now you plug in this n tending to infinity, and you see this limit 1 minus 1/2 times 1 divided by 10 to the power small n to the power capital N. And now the point is, doesn't matter how large n is, this goes to 0, but for fixed n or finite n, it will go also greater than 0. So 1 minus this number will be less than 1. And then if you take this value to power capital N, that n goes to infinity, and this was this way. So this one goes to 0, so the whole thing goes to 1. And that's it. That will be the end of the proof. Okay, questions so far? And what we need to do now is make some elementary computations. Basically, it's a little bit combinatorial, but not so easy to see and to compute this probability idea. Okay, so I used 8 minutes more, then I will stop on Monday 60 minutes earlier. See you on Monday. Thank you.